Hi everybody. So this is our very first video, and if you're following along with the calendar, you'll see that we actually start with 1.6. I rearranged the sections a little bit. So refer to section 1.6 in your textbook. 1.6 is all about graphs and tables of linear, quadratic, and exponential functions. And what I think I'm going to do is I'm going to break this up into two videos. This video will be particularly on graphs. And then the second video will be on tables. So let's look at the graph of a linear function. So we're starting with linears because chances are you all remember something about linears. So take a look at the word linear. Okay, it contains the word line. And so the graphs are straight lines. Okay, so what does that mean? Well, let's look at the different orientations that it could take. It could be tilted upward like this, straight line tilted upward. This would be considered increasing because we read a graph the way we read, from left to right. So we're going up the paper as we move from left to right. We could have a straight line but tilted downward. Okay, so we're coming down the page from left to right, and this would be considered decreasing. And then our third option for a linear function is that we have a horizontal line or a perfectly flat line, and this would be considered constant. It's not increasing, it's not decreasing, it's just flat, okay? There's no change, so it will be constant. And the concept of slope is the next thing we're going to talk about when it comes to lines specifically. Think about the word slope outside of math class, okay? When I think of the word slope, I think about skiing, okay? So what does that usually mean? That usually is talking about an incline or decline of a surface, okay? Or it's talking about the tilt of a surface, okay? Sometimes you might hear it called pitch, okay? But basically it's how steep something is. It's the steepness that is really being defined when you do slope. When you have an increasing line, you are going up, and so the slope is positive. These two things always have to mesh. They always have to coincide. Increasing lines with positive slope. If we are decreasing, we're coming down, okay? So it's a decrease or a negative change. So the slope is negative. And if you are staying flat, okay, you're not increasing, you're not decreasing, then we're saying that the slope is 0, okay? Be very careful that you don't say no slope. There's no such thing as no slope. There's always some way to describe slope. You might notice that the vertical orientation is missing here, okay? That's because a vertical line is not a function, okay? In one of the upcoming videos, we'll be talking about what it means to be a function, and then you'll understand why that's not included here. But these are the three orientations that a linear function can take on, okay? Let's continue with this concept of slope. In order to determine how steep something is, what does that depend on, okay? Think about climbing a set of stairs, all right? The height is important for a set of stairs, and also how deep the stairs are, okay? And we're talking about rise and run, okay? And again, all this might be very familiar. So we're talking about rise from point to point and then the run, or the horizontal distance from point to point. So we're going to use the letter M to signify slope, and we're going to define that as rise over run. But we're going to make a connection here. Not only is it rise over run, rise is in the y direction. Look at how I labeled my axes. We have our x-axis, we have our y-axis. X is always horizontal and y is always vertical. So rise is really the change in the y direction. Okay, so it's the change in y. And then run is really the change in the x direction. Okay, so again, if you're going to talk about it as like walking the line, it's how far up do you go between 2 points? So up and over, and then up and over, and you can maintain that same pattern, right? That same direction. The important thing that you understand about lines is that slope is interchangeable with something called rate of change. Okay, so again, it's how much you're changing each time. There's going to be a constant rate of change. So all lines have a constant rate of change. That pattern should be maintaining the entire time. So this is everything linear in terms of how the graphs will look. Okay, now let's talk about exponentials. So these are now graphs of exponential functions. An exponential function can look one of two ways. It can be increasing, which would look like this, or it could be decreasing, which would look like this. And there's a couple of very important things to note when it comes to these two different types of graphs. This one, yes, it's increasing, but it's also called exponential growth. And this one, yes, it's decreasing, but that's also called exponential decay. These types of relationships have been in the news a lot lately because they're talking about the growth of coronavirus, the spread of coronavirus. Okay, they talk about it as exponential growth. Okay, so we need to explore what's causing this pattern. Okay, what is causing this to sharply rise or sharply fall? Another thing to notice is that it will never touch or cross the x-axis, the horizontal axis. Okay, it always hovers right above and gets very close, but it never ever touches the x-axis, which means there's no x-intercepts. Okay, and that'll be defined in later videos. All right, so now what makes this happen? Okay, well, it turns out that there is something called a factor in exponential functions. I like to also call the factor the multiplier. Okay, the reason that an exponential function will grow so rapidly or decrease so rapidly is because each output is multiplied by the same value for every one change in input. So to put some values in here. If I look from point to point to point, 1 unit apart, okay? Because this part is very important. It can only be 1 change in input, at least for this level, at least for our class. We're talking about 1 change in input. To get from this output to this output, okay, I multiplied by some number, okay? To get from this to this, I multiplied by another number, all right? Let's actually put some values in a picture so that we can see what's happening. Let's say we have exponential growth, and it looks like this. Let's call this, I should move it down a little bit. Let's call this 1, 2, 3, 4, 5, 6, 7, 8. Okay. 0, 1 is where we're starting. Okay. And then 1 sits at 2. And then 2 sits at 4. And then 3 sits at 8. Okay. Let's think about what is the pattern that's occurring between these outputs. First, let's organize this into a table. I know we're doing tables in the next video, but let's organize it into a table. 0 has an output of 1, 1 has an output of 2, 2 has an output of 4, and 3 has an output of 8. Okay? I see that there's consecutive inputs, okay, 0, 1, 2, 3. I'm counting by ones. What's happening to the output? I'm multiplying by 2 every time. That's this idea of a constant multiplier, okay? Each output, consecutive output, is going to be multiplied by the same number every time. Okay. How are we going to figure that out from the graph? Well, factor, since it is a multiplier, to figure out multiplication, we're going to have to do division, because we know that those are inverse operations, okay? They will negate each other. So the factor is the output divided by another output, okay? So we're going to say it's an output of a point to the right divided by the output of a point to the left. And yes, it feels like that's backwards because we read from left to right. We don't do right first. But remember, this is the reverse of multiplication. I'm trying to figure out what the multiplication is. In order for me to figure out the multiplication, I'm going to have to divide in the opposite way. Okay? For example, we know that 3 times 4 equals 12. So 12 divided by 4 equals 3. Okay, do you see we have to reverse the whole thing? So that's why we're reversing this. So I'm going to take 8 and divide it by 4. I'm going to get 2. I'm going to take 4 divided by 2. I'm going to get 2. 2 divided by 1 is 2. Okay, so when we divide consecutive outputs, we get the factor. So we can actually put that in words as well. To find the factor, we divide consecutive outputs. Consecutive meaning the inputs differ by 1 only. Okay, so we have to be counting by ones for that to happen. Now, the reason that this was increasing is because my multiplier was a large number, okay? It was greater than 1. What do you think is going to cause a decay? What does my multiplier have to be? Well, let's think logically about this. I need to multiply by something that's going to make it smaller and smaller and smaller. The only thing that starts to cut things smaller are fractions or decimals. So my factor is going to have to be a decimal or a fraction. So now we have a few other rules that go along with exponentials. If the factor is a decimal, so it's stuck between 0 and 1, so it is a fraction or decimal, that means that we will have exponential decay. Or in other words, it'll be decreasing. If the factor is larger than 1, then we know that we're going to have exponential growth, or it's going to be increasing. Okay? Last but not least, when it comes to the graphs of exponential functions, or just the properties of exponential functions, there's something called a rate. The rate is the percent gain or loss. Now, we talked about factor as a multiplier, but you could also convert factor to a percentage if you wanted to speak about it in those terms. Factor and rate are complements of each other. Factor is the percent that you get to keep, and rate is just the percent change, okay? The percent increase or the percent decrease. So you could think about it that way. Your factor could be converted to the percent you keep, and your rate is the percent change, okay? And again, gain or loss, but it's the percent difference. So let's do a quick example. Let's use 1.2. Let's say we have a factor of 1.2. This would mean that we have exponential growth. If I converted this to a percent, I'm talking about 120%. The way you do that is you move the decimal over 2 spots. 120% is more than 100%. I don't want to count the original 100% because that's what I started with. So I take 120% and I take away the original 100%. And that tells me that there's a 20% growth because it was added on to 100%. If the factor was smaller than 1, so let's say 0.9, we'll use 0.9 as an example. If I converted this to a percent, that means every time I still get to keep 90%. Okay, I'm going to have 90% of what I had the previous time. But I don't want to know what I'm keeping. I want to know the difference. So if I take 90% and I take away the original 100%, I wind up with a negative value. I wind up with a loss. This tells me that I have 10% decay, okay, or it's decreasing 10% every time. I prefer that you kind of know this intuitively. That's why I'm doing it this way. If you want a formula for this, rate is always factor times 100, because we converted that to a percent, and then you take away the original 100%. Or if you don't want to think about it as percentages, you could do factor minus 1, because you still have to take away that original, and then you convert it to a percent, and it's times 100. But the bottom line is that rate is always going to be interpreted as a percent. Factor is usually not a percent, okay? So, going back to these two pictures, since this is increasing, I know that this must have a factor that is greater than 1 because it's the multiplier that's occurring. Since this is decreasing, I know that this must have a factor that is a decimal, okay, or a fraction. It's between 0 and 1 because I'm only taking a portion of what I had every time. This must be a positive percent change, okay, because I'm going up, I'm adding on more. This must be a negative percent change because I'm taking away as I move forward. So all of those things will go together. Now let's talk about quadratic graphs. So this is graphs of quadratic functions. A quadratic function, again, always has two orientations. I'm actually not even going to put this on a grid. Just going to show you what the two pictures will look like. These two pictures are always going to be the same. It's just a matter of where they're positioned on a grid, okay, on the axis. So this type of picture opens up, okay? This is a parabola that is opened upward. So it's like a cup. We talk about the opening and what direction the opening is, which means this parabola opens down. And I'm using the word parabola. So let's define that also. The graphs of quadratics are called parabolas. It's a vocabulary word, okay? And in essence, a parabola is a U-shaped graph, okay? Either face up or face down, just like we see in these two illustrations up here. All right, important features of a quadratic. Because of the change of direction, notice how it's decreasing and then it starts going back up in this example. Or in this example, it's increasing, I'm going up the page, and then it's going back down, all right? That means that there is a turning point. In this case, there is a minimum point. It's the low point, it's a valley. And in this case, we have a maximum point, okay? It is a peak, it is the high point, okay? Like a mountain. No matter which way it faces, these turning points are called a vertex, okay? The vertex is essentially the turning point, or it's the peak or valley, as we described, okay? But it is an ordered pair, okay? So it has to be a point on the graph describing this turning point on the graph. Okay, let me make a new sketch to give you a few more definitions. This time I am going to put it on an XY axis. Let's say we have a graph that looks like this. I can draw in a vertical line going through that vertex, and that creates a symmetry on the graph. I could fold right over this vertical line and it would be the same picture on both sides. So this vertical line is called the axis of symmetry. And when we learn about formulas, we're going to learn about how we can actually find the axis of symmetry. Okay. Notice that it crosses the y-axis. So parabolas can have y-intercepts. They will not always have x-intercepts. So let's look at 3 examples. I can draw the one that I just had. Okay, so let's look at one like this. I can draw one that looks like this. And I can draw one that looks like this. Okay? Good graphs are always labeled. Okay? This does not touch the x-axis. So this has no x-intercepts. Okay, it's sitting above, or if it was flipped over, it'd be sitting below, okay, but it doesn't touch the x-axis. This only kisses the x-axis. It only touches down on the x-axis. So this has 1 x-intercept. And in the last example, this touches the x-axis twice. There's 2 places where it crosses the x-axis. So this has 2 x-intercepts. Okay. You will have to know when a parabola is facing up or opening down. You will have to know whether it is decreasing or increasing. So make sure that you'll be able to follow the graph in those ways. So now let's do some problems. These are pages directly from your textbook. So if you just follow along. Okay. We have this graph, right? We're being asked to decide, let's read the instructions. Decide if it's linear, exponential, or quadratic, and then identify the important features. So here we have this arc. Well, that must mean that it's a quadratic. Quadratics are what change the direction, okay? So this is definitely a quadratic. Important features. Which way does it open? Does it open up or does it open down? This is like a mountain, okay? The opening is down here. So this opens down. Can we find the y-intercept? The y-intercept is where it crosses the y-axis. So this point right here would be the y-intercept. Can I find the x-intercepts? That's where the graph will cross the x-axis. There's 2, here and here. Can I find the vertex? The vertex is right here, and that would be the point 2, 3. So 2, 3 is our vertex. Okay. Notice that the axis of symmetry is cutting right through 2. And we would say that it's the line x equals 2, okay? Because it's sitting right there at 2 on the x-axis. All right, next picture. Look at the graph and decide. This is just constantly going upward, okay? There's no bend, it is a straight line. So this must be linear, okay? Important features about a linear. Well, we need to know x-intercept, y-intercept. Okay, those are points you can just pick out. We need to know increasing or decreasing, and we should be able to figure out how it is increasing or decreasing, that rise over run. So, y-intercept, 0, -3, okay? X-intercept, 2, 0, okay? These are the points on the line where it's crossing each axis. Is this increasing or decreasing? As I follow along the page, it is going up. It is increasing. How do I walk from point to point? Well, I'm going to rise 3, and I'm going to run 2. So if I do rise over run, it's going to be 3 over 2, or if I convert to a decimal, it's going to be 1.5. That tells me there is a constant change. Every time I go up 1, or I'm sorry, over 1, I'm going up 1.5. So over 1, up 1.5. Absolutely. Over 1, up 1.5. Okay, that should be a constant change. Next graph, and this will be the last example for, well, second to last maybe, for this video. This starts out and then shoots up, okay? That looks exponential, okay? Is it exponential growth or decay? This is going to be exponential growth because it is going up as I go from left to right on the page. How can I figure out the factor? I'm going to look for 2 consecutive points, 0, 3, which also happens to be the y-intercept, and I see the point 1 and 4.5. Okay, so this is the point 1 and 4.5. And it does have to be an obvious point. You don't want to approximate these. Okay, so we have the point 1, 4.5. I want to divide 4.5 by 3 to find that multiplier. So that's the work that I'm going to do. I'm going to divide 4.5 by 3 to figure out that multiplier. The multiplier here is 1.5. That means that for every 1 change in x, the output is multiplied by 1.5. So keep in mind, it's different from linears. Linears are a constant change. It's a constant addition or subtraction. This is a multiplier. And last but not least, if I find out that the factor is 1.5, what is the rate of increase? This means I'm keeping 150% if I were to convert this to a percent. I don't want to count the original 100, so if I take away the original 100, that means it is increasing at 50%. Okay, I want to do a decreasing one too. This will be the last one for this video. Here I have an exponential again because it's sharply coming down and then it's tapering off, okay? It doesn't change direction, so don't confuse it with a quadratic, all right? It's just constantly going down and then hovering. I want to know what the factor is. I have to do the same thing, consecutive outputs. This is the point 0, 100. Also happens to be the y-intercept, okay, an important feature. They're showing me that this is the point 190. I do have a difference of 1 here, so I can divide consecutive outputs. Remember, you divide in reverse of the way you would normally think. You're going to go from the rightmost point to the left. So 90 divided by 100. If I take 90 divided by 100, I get 0.9. Does that make sense? Yes, because it's a decreasing exponential. My factor was supposed to come out to be a decimal. I'm emphasizing that because if you divide backwards, you're not going to get a number in the right range, okay? A decreasing exponential is supposed to have a decimal factor. So make sure when you divide, you're getting a decimal. If you're not, you're probably dividing upside down. If I convert this to a percent, that means I'm keeping 90%. But I don't want to know how much I'm keeping when I talk about rate. I want to know what the change is. So if I'm keeping 90%, that means I am losing 10%. And so this is decreasing at a rate of 10%. Decreasing by 10% is the same as keeping 90%. It's important for you to understand these relationships about percents. Okay, I know this was a lot. I hope this all makes sense. You can always ask questions when we meet live, and I will see you in the next video.